All right, so let's see if we can develop a theory for fluxes through surfaces that are functions. And what do I mean that are functions? Because
surfaces in their own, like,
yeah.
bounded.
Which means we would have to find a normal vector to.
How about that are functions of x and y? Okay.
So,
So here's my idea. Let's see, what were we doing? We were doing d areas, right? And we were thinking, okay, a d area is a n dotted with dA.
Yep.
And that was me really thinking, okay, the change in area as a vector is about the normal vector times the size of the patch you're talking about, right?
Yeah.
Okay, so I actually know a thing that looks like a unit vector that comes with a size. So you just have to remember this. Remember the cross product?
Yeah.
Geometry?
Geometric version.
Uh-huh. So what was the geometric version of a cross product? So if I said like, is
So if we-
V cross W,
so if we're crossing dx and dy.
kinda, yeah. That'll sort of work.
Mm.
It's just a tiny hint more complicated, but it's pretty darn close.
Crossing that is.
So if I had two vectors, V and W, right?
Mm-hmm.
What's the cross product tell you about them? You take
the
V
area of the
cross W,
parallelogram.
it's the area of the parallelogram, right?
Yeah.
So remember this, there's three things about this, right? That cross product vector is perpendicular to both V and W, right?
Mm-hmm.
Yeah.
Its length
Is one.
is not one, but is the area of a parallelogram. This thing, where this is V and this is W. And then what's the third thing?
Follows the right-hand rule.
Perfect, follows the right-hand rule. Okay, I give exactly 0 craps about the fact that it follows the right-hand rule right now.
Yeah.
I do care that it's perpendicular to both, right?
Mm-hmm.
In this context, what does that mean?
It'll give us.
It when that cross L equals 0.
It's going to be the normal, right? And then its length is,
It's supposed to be
It's gonna be
one. All area of the parallel. All tilt.
the change in area, right?
Oh.
So if I had a surface, right, that was determined by a couple of vectors, then I could cross the vectors and I would automatically get that D area thing I'm looking for. You guys see that? Okay, so I want to think about surfaces that are functions, right? And I want to use this trick. So here's a surface that's a function. Look at this, think of f of x and y.
Oh, you're in Gin's room.
That
You need
doesn't
to be
start
in
till
here
5.
now. It doesn't start till 5.
No.
Yeah.
Okay, so the two vectors that determine this thing are made by slicing this way and this way, right?
Windows.
Okay, see that little patch?
Mm-hmm.
Okay, so let me think about those as vectors. This thing, this surface, that's R parameterized by x and y, right? What are the inputs and what's the output? Do you need to be in here now?
We're gonna start a final at 4,
Okay,
at your convenience.
yeah, thanks.
Oh, they're already at their
And the
Function of
output
x and y.
is f of x and y. You guys see that?
Yeah.
So your partials, right, Rx, that's going to be this vector here. Oops, yeah. You guys see that? And Ry is going to be that vector there.
Yeah.
And you just cross them. And because I'm out of time and
Just got a normal vector standard.
and Jim needs to be in here. When you take these, right, you get the vector 1, 0, fx. And when you get Ry, you get 0, 1, fy. Right?
Yeah.
And so what you find out of this thing is that d area in another form is minus fx, minus fy, and 1. dx dy. Cool?
We'll have an example later.
Yeah, and I'll give you an example next time we meet.
Yeah, what happened to the end?
Remember that n was given by the pointiness of this, and the
that was
size
d8
was given
vector,
by the
sorry.
length. Cool?
I didn't catch the vector half.